Hello there, welcome to my channel on chemistry lessons. This channel provides full lesson content and full lesson videos on all chemistry topics for AQA, A-level chemistry and BTEC applied science. I will be uploading regular content. Initially it'll be full lesson content, and as we get closer to the exams I'm going to be looking at focusing on key concepts and exam technique. So please subscribe so you don't miss out on future content, and also use the comments features to let me know what you think of the videos and any future videos you think would be useful. Good luck. This is an AQA A-level chemistry video and it's a second year topic. It's organic and it's the first lesson of 2 on condensation polymers, spec point 3.3.12. Before we move into the A2 topic though, we should probably remind ourselves of the AS topic on addition polymers, which is also a little bit touched upon in your GCSE. So an addition polymer is when we have an alkene as a monomer, where you have 4 groups attached to your monomer. I just label them A, B, C and D. So the idea addition polymer is from an alkene, and what can happen is they can join end on end and form a long chain, and that would be 2 of these stuck together. So I've drawn a repeating pattern of 2, or a repeating chain of 2. We can just show it in square brackets as 1, like this, and we can draw a little N on the side of the brackets and put an N in front of these monomers. And that's all that happens. That double bond opens up and allows them to join end on end. And these 4 groups remain completely unchanged. These 4 groups will still be here. So we'll have an A and a B, an A and a B. So this would repeat over and over again. A, B, A, B, A, B. And along the bottom, C, D, C, D, C, D. So that's 2 repeat units. You could be asked to draw 3 repeat units in the exam. You could be asked to draw 4 repeat units. You could just be asked to draw 1 repeat unit. So just look out for the terminology in your questions there. Likewise, be prepared to go back over. So you could be given the polymer and you could be asked to identify the monomer. Just remember that a monomer will always have this carbon-carbon double bond. That's the focus point there. And your repeat chain has these carbon-carbon single bonds. So do not get distracted by these side groups, because they will try and do that to you. Okay, the backbone is right here. There's your backbone of your addition polymer, through the middle there, through the middle. These side chains can vary quite dramatically, and quite a broad range of different side chains, which is why you have different properties of addition polymers, because those side chains will affect the properties. Okay, and one last point on this then. These types of polymers are very, very strong. They don't biodegrade because the backbone of the polymer, the backbone is strong carbon-carbon covalent bonds. And you'll see the polymers we look at today don't just have carbon in their backbone. So addition polymers only have a carbon backbone. Carbon-carbon bonds are very strong. So these types of addition polymers, do not biodegrade. Right then, so as I've said, this is lesson 1 of 2, and this is the spec point it's going to focus on. So we're going to look at condensation polymers now. Okay, we've just done a little recap of addition polymers, which is an AS topic. This is looking at condensation polymers, which is a different type of polymerization. Okay, so there's 3 scenarios that we're going to look at today. The scenario of dicarboxylic acid with diols. Then we'll look at dicarboxylic acid with diamines. And finally, we'll look at some amino acids. We won't do an awful lot of amino acids here. We will just make the link between amino acids and polymers. Okay, there is an entire topic later on in A2 chemistry where we will look at amino acids and proteins. And once we understand what these polymers are, we're going to look at some specific examples. So we're going to look at some specific examples of polyesters, which is one of them. We're going to look at Terylene, and we will look at 2 specific polyamides, which is Nylon and Kevlar, and we're going to look at their properties and look at their structures. Okay, and you can see this is always the best bit to look at. The bottom explains what you should be able to, the skills you should have. So we should be able to draw repeat units for monomers. we should be able to draw repeat units from a section of the chain. So again, similar to what we've just done there with addition polymers, and we should be able to do vice versa. We should be able to identify monomers from polymers. Okay, and then finally at the bottom here, it talks a little bit about intermolecular forces. So again, that's going to be a bit of revision from AS. Right, so polyesters is something we're going to look at. So let's just remind ourselves of what esters are. So an ester link is where we've got that. That's the functional group of our ester link. An ester is a carbon double bonded to an oxygen with an OH. And quite often we make these from carboxylic acids. We saw that if you take a carboxylic acid and you react it with an alcohol under sulfuric acid, we could undergo esterification. So we've seen making esters before. This ester link isn't new to us. We've also seen making esters from acyl chlorides. So there's two ways we've seen that we can make esters. We can make esters with acids, or we can make esters with acyl chlorides. We actually did the mechanism for this one because again this was with an ROH group, and this was that nucleophilic addition elimination. There was no mechanism required here. So we have seen esters before. Okay, so esters and polyesters. Polyester is just literally lots and lots of esters in a row. It's lots and lots of esters in a row. So amides then. What's an amide? And again, we've seen amide links. Amide link that was an amide link. And we made amides when we did our acyl chlorides with ammonia or acyl chlorides with amines. So again, you've seen that, and we did the mechanism. That was your acyl chloride, and this was with an amine. And again, it was the same, exact same mechanism, your nucleophilic addition elimination, and you would make your amide. Call that R dash dash, and you would make your amide. Okay, so we have seen this. This is a good time to make links in organic chemistry. The more you can weave it all together and make links between the topics, suddenly there's an awful lot less to remember. Okay, because the chemistry in polyamides isn't going to be too dissimilar to our reactions with amides or how we made amides. Finally then, our prior knowledge on intermolecular forces. There were three types of intermolecular forces. We had dipole-dipole, we had hydrogen bonding, and third, the very poor van der Waals. Okay, so it is worth reminding yourself of what those forces are and when they arise, because we will look at these forces between polymer chains and we'll be looking at these three types of intermolecular forces. So again, that's way back when, at the very beginning of AS. Okay, so let's look at our first example of a condensation polymer then, and we'll look at where the name comes from. So a polyester from a diol and a dicarboxylic acid sounds really complicated, but what I'm going to do is I'm going to try and simplify it down. So I'm going to have a diol, which is basically an organic molecule with two OH groups. So that bit in the middle is just something, I don't care what it is, it's just an organic molecule. And they'll change this, this could vary, but there we go, there's a diol. And now let's draw a dicarboxylic acid. Again, I'm going to put a little block in the middle. So it's a dicarboxylic acid, basically means it has two carboxylic acid groups on the same molecule. They don't necessarily have to be at opposite ends, but there we go. There's a dicarboxylic acid and a diol. Now, if we were to react these two together, what can happen is one carboxylic acid can react with alcohol over here and form an ester. But then what can happen though is another one of these can come along and join to the other end. So you literally have a carboxylic acid. So let me try and draw this out. So if I was to just draw two of them coming together, I'll just draw the product of one esterification. So I'd have my carboxylic acid, but then it will be bonded to the O, releasing water. So water would be released, the OH and the H, and this would leave me with an OH here. So that would be an ester. However, if I've got lots and lots of these dicarboxylic acids and lots of these diols, what's going to happen is we're going to end up with numerous ester links. It's going to end up with another carbon. There we go. Another one of these. Slightly annoying. That's a different shade of blue, isn't it? Damn. Never mind. So there's another carboxylic acid. And I could go over and over and over again. I could take another alcohol and put it on here. And I could just repeat this over and over and over and over again. I could just join them end on end on end on end, and I'm going to end up with a polyester. I've just got lots and lots of ester links, and they're all joined together. Diol, dicarboxylic acid, diol, dicarboxylic acid, and this time you can see the backbone. So this would repeat many, many times, and your backbone not only contains carbon bonds, carbon-carbon bonds, it also contains ester links, hence the term polyester. Okay. Now, it doesn't get any more complex. It doesn't vary from this. The only thing that's going to change here is going to be your kind of orange blob, like what's in the middle there, and your blue blob, what's in the middle there. You just literally imagine these as two Lego bricks. So you've always got to alternate between the blue and the orange and the blue and the orange and the blue and the orange. It's just an alternating, repeating pattern. No more complex. And every single link that you make releases a H2O. So for every single ester link, you're releasing H2O. Hence the term condensation, polymerization. You are releasing a small water molecule. Now this is very, very much the same for polyamides. So if we look at a diamine, so this time my diamine, it's an amine group is an H2. Just put a red blob in the middle there. It's a molecule that contains two amine groups. And I've just separated them by the red blob. The red blob is the rest of the molecule. And I'm going to stick with the blue. I like that blue. Let's get the same shade again. I'm going to have carboxylic acid separated by something. There we go. And now what can happen is we form an amide link. So I'm going to draw one carboxylic acid on the left here. Blue bit in the middle. And we're going to have an amide link. So the amide link now, NH, red bit, NH2. So that's one amide link. And in doing so, we've released a water molecule. So that's just forming the amide link with the carboxylic acid. No mechanism is required here. But what can happen is we can get another acid to come along and form another amide link here. Get the right shade of blue this time. Yes. So we go. I've stuck another one there, look. So I've now got two amide links, and I can continue to do that hundreds of times, which would leave me with a polyamide. Notice how for both of these types of condensation polymerization, I've got two different monomers. It's not one monomer, I've got two different monomers here, and they're joining end on end to form a long polymer chain with an amide link in the backbone. So there's the backbone of my molecule. That would repeat several times. I could draw one repeat pattern here. So why don't I have a go at drawing one repeat pattern? So one repeat pattern would have one carboxylic acid in it with my amide link. That would be one repeating unit. that would just repeat several times. I've got one of each monomer in my backbone, or in the backbone there. So the backbone consists of carbon-carbon bonds, plus whatever bonds these are, I guess, because we don't know what these are yet. That's the only way they can make these more complicated in the exam, is by making them look complex and complicated. We are going to look at some specific examples later, Terylene, Nylon and Kevlar. So there are three that you actually need to know, these middle bits. The rest of your exam questions will be just based upon molecules they give you. We can't predict what they'll be, but you know, don't be confused by what's in the middle. Dicarboxylic acid, diamine. Sounded quite aggressive, that. And finally, I don't want to do an awful lot here, but we do a full topic on amino acids. But an amino acid it's a molecule that has a carboxylic acid group and an amine group. That's an amino acid. It's a group amine, amino, acid, acid. And they're separated by one carbon. People that do biology have probably come across this already. We will look at them in detail later on. But what can happen here is they can literally join end on end together. So if you were to have lots of these, they can form amide links with themselves. That would just repeat over and over and over. They could just join end on end on end. Okay. Now, the likelihood is in proteins you have several different amino acids joined together, so it won't just be the same one. And that's what proteins are. Proteins are a sequence of amino acids. We'll look more at that in detail when we do the biochemistry topics later on in year 2. So that's just an example of a polyamide, I suppose. It's an example of a polyamide, but just from the possibility that the molecule could have an amine and an acid group on the same molecule. Let's take a look back at the spec then. So we very briefly looked at the first 3 bullet points, which is condensation polymers from dicarboxylic acids with diols, dicarboxylic acids with diamines, and amino acids. So what we're going to do now is I'm going to try and take an opportunity to test us on those 3 whilst we look at these 3 specific examples. We're going to look at 3 specific examples. You do actually need to know the structures of these, unfortunately, so it's probably worth making yourself some revision cards on Terylene, the structure, and particularly the nature of the intermolecular forces. And also we're going to look at Nylon 6,6, there's a bit of a clue in the name, and we'll look at Kevlar. Okay. So what I'm going to do is I'm going to draw a repeating unit of Terylene, and you're going to try and identify the 2 monomers. So I'm going to draw one repeating unit. What I suggest you do is you try and identify the 2 monomers that would be needed to make this. Bit of a hint, we know it's a diol and a dicarboxylic acid. That's the only types of polyesters that we're looking at. Now we can identify this as a polyester pretty quickly because it's got ester links in the backbone. There's the backbone of the molecule, of the polymer. Okay, so we know it's going to be a dicarboxylic acid, and the easiest way to do this would be to break our ester links. Okay, so find the ester links and break those ester links off. There's an ester link and there's an ester link, and suddenly the dicarboxylic acid should be fairly straightforward to spot. So there's my dicarboxylic acid. So one monomer will look like this. Benzene ring. It is literally 2 carboxylic acid groups separated by a benzene ring. There we go. So that would be one of our monomers. The other monomer we know is going to be a diol, and the diol is going to be there. Now this O could just be on, there we go. So it's our diol. So 1, 2 carbons. So it's ethane 1, 2 diol. That's benzene dicarboxylic acid. So So there's our two monomers. Now, this here, we call it terylene. Sometimes you'll hear it called PET, polyethylene tetraphthalate, or PETE. So it goes by a few names, but our spec call this terylene. And once we've looked at the structure, we're going to look at the structure of polyester and nylon. Sorry, we're going to look at nylon and Kevlar. And once we've done that, we'll come back and we'll compare the properties of those three. Okay. So what's Kevlar? Let's have a look at the structure of Kevlar. So this time I'm going to draw the two monomers, and you're going to draw the polymer Kevlar. So I'm going to draw the amide in red, which is a really badly drawn benzene ring there. It's broken. There we go. And a dicarboxylic acid. Start to make some links here, because the dicarboxylic acid is the same here as it was in terylene. And in fact, these two look very similar to each other. We've got a dicarboxylic acid and a diamine, literally both of them separated by a benzene ring. So you try and draw the structure of the polymer then. So there's our dicarboxylic acid. Show the amide link. There we go, that's a repeating pattern. Now, there was nothing stopping me really from putting this NH on this side and leaving it out here. It just has to be a repeating pattern. Okay, so there's my diamine and my dicarboxylic acid used to make Kevlar. And again, at the end, we're going to compare Kevlar, nylon and terylene in terms of their properties. We've got one more to look at though. Right, this is often called nylon 6,6, and that helps actually when we call it nylon 6,6, because it helps to identify or to remember the structure, because we do need to remember these three structures here for nylon, Kevlar and terylene. So the 6,6 structure, that is literally, it's a diamine separated by 6 CH2 groups. There's 6 of them. So there's 6 carbons long. It's a 6 carbon chain with NH2. And likewise, the carboxylic acid contains 6 carbons. So we're going to have 6 carbon long, this chain. Be careful, oops, OH. Be careful, this would be CH2 4. There's only 4 CH2s there because we've got a carbon here and a carbon here. So it's nylon 6,6. It's a polyamide, and the carboxylic acid and the diamine, the dicarboxylic acid and the diamine both contain 6 carbons. So what does this chain look like then? Let me draw this polymer chain out. I'll put NH. And this will have you've probably noticed that I've made a mistake up here, look. I said that it was 6 carbons long, I've written 2. Fantastic. I think we'll leave that in the video though, because it's good. Sometimes even superhumans make mistakes. So why have I put a 2 down there as well? You can tell it's late, can't you? I haven't had my tea either. And I've done this. What am I doing here? Do you know what? It's staying in the video because you'll probably find it funny. Good. You've seen me make 2 mistakes at the same time in the same video there. Well done. But I spotted them. That's the important bit. Right. Let's get this chain done. That's a 4. Yes, it is. There we go. And that took my time, didn't it? So that's now the structure of nylon 6,6. We do need to know, we need to remember these structures for Kevlar, nylon and terylene. It seems pretty seems like a bit of a task. However, the nylon 6,6, that definitely helps. You know, it's a polyamide and they're literally just 6 carbons long. The Kevlar was just your 2 benzene rings between your two amides and your two carboxylic acids. And when we looked at the first one, which was Terylene, it was 6. What was it? It was a benzene ring between your two carboxylic acids, and there was 2 carbons between the 2 alcohols. So there was only 1 polyester, and that was your Terylene. Let's compare these 3 structures then. So here we have our 3 polymer friends, our 3 examples. So what you might want to do is, before I do it, you might want to pause the video and see if you can remind yourself of which one is which one's Kevlar, which one's Nylon 6,6, and which one is Terylene. Well, Terylene was our example of a polyester, and only one of these is a polyester, and the bottom one is Terylene. And the other 2 are examples of polyamides. One of them is 6,6 nylon, or Nylon 6,6, and that is this one. This is nylon, often called Nylon 6,6. I would remember the name Nylon 6,6. It definitely reminds or helps it to remember that 6 carbons long in that chain, and then we've got 6 carbons long between the 2 ends. So you've got 6 carbons between the 2 carbonyls. Remember that these are included in the 6, which is why I've got 4 CH2s. And the final one is Kevlar. And now, when we look at the intermolecular forces, usually in addition polymers, which we looked at earlier, which is a review of first year, usually you only end up with weak van der Waals between addition polymer chains. Now, in amines in particular, these 2 amines here, polyamides, so in these 2 polyamides, you're going to have strong hydrogen bonding taking place between polymer chains. So if you imagine if you've got another chain here, you're going to have hydrogen bonding between the polymer chains, which is a very strong type of intermolecular force. That means that things like nylon and Kevlar we have strong bonds between. They can pack very tightly and will form very strong bonds between the polymers, and therefore that's why Kevlar is actually used in a lot of protective clothing for motorcycles and helmets and things. And nylon is a very, very hard wearing man-made fibre. Okay, now Terylene, you won't have hydrogen bonding in Terylene, but we will have some dipole-dipole going on. Okay, so you are going to have stronger intermolecular forces in these condensation polymers, in particular these polyamides, because of the hydrogen bonding. So be prepared to talk about intermolecular forces there. But again, if you're up to speed with your AS intermolecular forces, that's fairly straightforward. So that actually covers all spec points up to here. Okay, we've covered all the spec points. Admittedly, I've made this very simple, and in practice you will find some complicated examples, but keep your eye on the prize. I always like to say is that it's always going to be the same. They're only going to make this difficult by those middle bits, by those bits that they put between the 2 ols and between the 2 amines or between the carboxylic acids. It's the only thing that makes that difficult. Okay, this bit here is screaming out for revision cards. Okay, this bit here is screaming out for revision cards. So a little bit of research here. Make yourself 3 revision cards, 1 on Terylene, 1 on Kevlar, 1 on nylon, and then remember those structures. So things we should be able to do: draw repeating patterns, yes. Draw a repeating pattern from a section of the polymer chain, yes. Can we draw the structure of the monomer if we were given the polymer? Yes. We're going to practice a bit of that now. We're going to do some exam technique, okay, and looking at intermolecular forces. Yes, we've done that. So we'll move on to some exam questions now. Okay, now it's time for you to have a go at a few questions. So pause the video. This should take in the region of 4 or 5 minutes. So pause the video, and when you're ready, unpause. Okay, so we've got 2 polymers, P and Q. And first thing I would do is I would have a look at the backbone of the polymer, and then you can decide whether it's a addition polymer or a condensation polymer. And if it is a condensation polymer, is it a polyamide or a polyester? Well, P, that just has carbons running through the backbone, so that has to come from an alkene. That's an addition polymer. Polymer Q, that has ester links, so there's oxygen in that backbone, so that's a polyester. Right, let's try and answer the question then. So draw the structure of the monomer to form P. Well, I've already said that I've identified that that must have come from an alkene because it's an addition polymer. Okay, that's why it's always useful when you do an exam. Usually, if you read the first few sentences, you can try and work out what they're going to ask. So a good exam technique would be to read the exam question, and then what you do is you start thinking about the things you know about those. Okay, so now I've got to make sure I put the correct groups on here. There's a CH3, a Cl, a H, and a CH3. And the type of polymerization is addition. Fairly straightforward, 2 marks. Part B, draw the structures of the 2 compounds that react together to form Q. So we need to form this polymer, and I know it's going to be from a dicarboxylic acid and a diol. So what I suggest you do is find the 2 carbonyl groups. So there's my 2 carbonyl groups, and those are going to be your dicarboxylic acids, and then you find out what your block in the middle is. So what I've got here for my dicarboxylic acid, so there's 1 carboxylic acid, and in between there's a CH2, and then there's a C with CH3, CH3, and then that goes to another carboxylic acid group. So there we go. Now obviously there's several ways you could have drawn that. I could have drawn it the other way around, like the mirror image of it, I suppose. I could have drawn skeletal. So there's more than one way of doing that out there, but you can see what I've done is I've identified that middle block, and that was my middle block there between the 2 carboxylic acids. So the easiest thing to do with either polyester or polyamide is to identify your 2 carbonyls, draw your 2 carboxylic acids from those carbonyls, and then draw the middle section. And once I've taken care of that, the rest of this polymer chain is made up of the diol. So where's the diol? Well, that O was an OH, OH. So my diol, there's a C, H with a CH3. And then the next section is a C, H, CH3. So there we go. Okay, next question then. So again, this is looking at around about 5 minutes for this one. So have a go, and when you're ready, unpause the video. Okay, so we've been given some repeating units of 2 different condensation polymers. And yes, they are condensation. I can look through the backbone. This one's carbon, carbon, oxygen. This is a polyester, and this one, it's got amide links. So we've got polyamide. So the type of condensation polymer, well, this is a polyester. And the common name, well, that's suggesting it's one of the ones I'm supposed to know, because there was 3 we were supposed to know. We were supposed to know the nylon 6,6, where the 2 carboxylic acids and the 2 alcohols were separated by 6 carbons. It's not that one. We also need to know Kevlar, which Kevlar was separate between 2 benzene rings and it was a polyamide, so it's not that one. And the other one was Terylene, and that Terylene was where we had a benzene ring between the 2 carboxylic acids and you just had 2 CH2 groups between the alcohols. So the common name for this was Terylene. Also, you'll see it sometimes referred to as PET. But you'll see that in our spec it was referred to as Terylene, so that's the one I would expect you to remember. You don't need to remember both. Next one, type of condensation polymer here. This is a polyamide, and the common name for this one, Kevlar. Because in Kevlar we had the diamines separated by a benzene ring and the dicarboxylic acid separated by a benzene ring. Explain why polymer in part B2, that's this one, has a higher melting point than this one. Okay, well, that's because Kevlar will have hydrogen bonding due to the NH groups, which requires more energy to break. Simple as that. So you're identifying hydrogen bonds are present in Kevlar and therefore more energy is needed. Words to that effect. Next question then. So we're looking at about 5 minutes here as well. So pause the video and when you're ready, let's go through it. Okay, so we've got an amide or peptide link. We were calling them amide links, so you can ignore this peptide link for now. We will come back to that when we look at amino acids. Draw the repeating unit of the polyamide formed when the reaction of propane dioic acid with hexane 1,6-diamine. Well, let's identify what these things are. So propan dioic acid, well that's pro is 3, dioic acid means there's 2 carboxylic acid groups. They must be on each end because you can't have a carboxylic acid group in the middle because it's already got 2 bonds, look, so it can't be there. So that's going to be propane dioic acid, which means the block in the middle is simply a CH2 group. And 1,6-diamine, well that's a diamine with 6 CH2s between them. You could draw the full chain out. There's no reason why you shouldn't. But I'm just going to do CH2 6. Don't have to do it this way. If you really wish to draw them all out, go for it. And that's NH2, so it's diamine on the 1 and the 6. Well, actually, it's probably a better idea if I put 4 in the middle and then actually show the amine group at the end. Either or, actually, I could have left it as 6, but I've changed it now, so I'll leave it. As you can see, you don't have to be absolutely, there's not one absolute answer, there's several ways of doing this. Again, I could have used skeletal because it hasn't specified. Just be careful, because sometimes in exam questions they will specify that you must use displayed or you must use skeletal. Just be careful there. Okay, and now I'll identify the block in the middle. So the block in the middle here is literally 6 CH2s. Okay, so I'm going to draw my repeat unit now. I'm going to start, doesn't matter where I start, there's several ways of doing this. I'm going to start with my acid group. So I'm just going to draw the carbonyl and then I'm going to separate them with the CH2. And I've got my other carbonyl. And now I've got my ester link. So let's draw the ester, which, oh, sorry, not ester, amide link, and it's an NH. One of the H's is gone, but we've still got the NH. And then I'm actually going to put CH2 6 this time, and then it goes to NH square brackets. Just be careful because sometimes you'll see that people will put the N here, and that's fine. And if you put the N here, that's absolutely fine, but you can't have, so if you put the NH here, you must remove it from this end. Because what you've got to remember is that this end, you've got to visualize this end being stuck again to this end, so that's your repeat unit. So that's also correct. Okay, so there's several different ways you could draw that. Several different ways. My OCD likes me to have it nicely side by side, but as I've said, be prepared to see it in different ways just in case in a question they give you it in a slightly awkward way, because they will do that sometimes. So that's my answer there. In terms of intermolecular forces between the polymer chains, explain why polyamides can be made into fibers, whereas polyalkenes usually produce fibers that are too weak. Right, well that's the intermolecular forces question, isn't it? Okay, so here we can say that polyamides will have hydrogen bonds between polymer chains, whereas polyalkenes will only have van der Waals forces between polymer chains. And van der Waals forces are much weaker than hydrogen, therefore they are much weaker fabrics or fibers. One last question then. So this is again another shortish one, just a few minutes here, but pause the video and when you're ready, unpause the video. Right, name compound Y, the dreaded naming ones. Right, okay, so what have we got going on here? We've got an OH group to a CH2, to a CH2, to the good old Q group. Okay, now we've got two functional groups going on here. We've got an alcohol group and a carboxylic acid. Hopefully you're aware that with an alcohol group, you can have a prefix and a suffix. You can use the suffix -ol or the prefix hydroxy. Okay. Now with a carboxylic acid, we don't have that prefix. So we're just going to call this propanoic acid. So it's going to be propanoic acid with a hydroxy group. And it's going to be 3-hydroxy propanoic acid. I'll see a common mistake there where people will almost get there, but they'll call it 1-hydroxy propanoic acid. It's definitely not 1-propanoic, because as soon as you identify it as a carboxylic acid, this becomes your number 1 carbon, because it's your carboxylic acid carbon. That's your number 1 carbon. Therefore, the hydroxy is on the 3rd carbon, not the 1st. Okay, has to be 3-hydroxy propanoic acid. Under suitable conditions, molecules of Y can react with each other to form a polymer. Okay, so what's happening here then? So it's saying it can react with each other. We haven't seen this. Okay, they're trying to push us a little bit here. But let's try and keep our eye on the prize. The main thing is we've got an alcohol group and a carboxylic acid group that can join to each other. So this is just going to be one monomer here joining end to end with itself. So I'm going to draw one unit in red. So there's the O from the alcohol. Look, I'm going to leave it on that end there. C. That would be one repeat unit. That would just repeat over and over again. Okay, so that's one repeat unit. So what I need to do is just draw another one of those, and I'm home and dry because it wants 2 repeat units. I've been quite specific here. Okay, so I now need to draw this again. So O, C. Got all Spanish, haven't I? So that would be 2 repeat units. Do you agree? Sí, señor. There we go. I've done 2 repeat units. Be careful that you read the question, okay? RTFQ. Read the full question. There we go. That's 2 repeat units. And the type of polymerization here is condensation. Polymerization. Beautiful thing. And that brings this lesson to a close. I think I'm sadder than you. Hopefully the sound quality was an awful lot better on this one. It's an upgraded mic after a few complaints I got, so there we go. Hopefully that's sorted. It's definitely worth practicing on this one, to practice identifying monomers from polymers, polymers from monomers, because that's basically what you're going to be asked to do here. Okay, you're going to be asked to identify monomers from polymers, or polymers from monomers, vice versa. 1 repeat, 2 repeat. Is it polyamide, polyester, addition, and then the intermolecular forces and how they affect the strength of these fibers, and then also make sure that you know the structures of your Kevlar, Terylene, and Nylon 6,6. Good luck. Quite a long video this one, but again I'll put together a short snappy revision version of it with the key concepts for just before the exam, so you know where it's at. So make sure you subscribe so you don't miss out on those future updates. Hopefully the quality is getting better as well. Over and out. Good luck.